In Florida, there's a special lab studying lightning. ABC's Bill Blakemore went to pay a visit.
At any one moment, there are about 2,000 electrical storms on our planet. It's a constantly crackling ball of lightning, about 100 bolts a second, striking people, houses, power line, airplane.
Normal commercial plane about twice a year.
All right, so it's twice a year. Normal commercial airplane getting hit by lightning. Twice a year. And you're perfectly safe while you're on the inside, right? So the question is why? We discussed this roughly about 5 times. All right, so let's discuss it one more time. So you're on the inside, airplane is getting struck by lightning, and you are perfectly safe on the inside. Why?
You say it was a floating cage?
Okay, so what does it mean?
Isn't it that all the electricity passes through the conductor and then would get ground through eventually?
Okay, I'm gonna give you 5 points for that one. So the outside is metal, right? And you're on the inside, and you're perfectly fine. So the question is why? At this point, guys, even if you don't, I mean, we haven't really started the new chapter yet, but you kind of have an idea, right? You should be able to actually come up with some kind of a justification as to why you should be safe. Why would you be safe inside a metal conductor? Your initial thought was, hey, there was an insulating material between you and the metal of the airplane. Well, get rid of that insulating material. Put your hands on the metal of the airplane from the inside. Would you be fine if that's the case under the circumstances? Case in point.
In Florida, in Glenview, high winds took down a power line, trapping a woman inside her car. Police did not know if the wire was live, so they ordered the woman to stay inside the car to avoid contact with the ground. Then they shut down the entire intersection. The driver was trapped for nearly 2 hours until a ComEd crew showed up.
I called the fire department and told her to stay in the car and not to move and not to attempt to get out of the car. So
How was she handling this?
well, at first she was crying and she was pretty hysterical and she was talking to family members on her cell phone.
ComEd crews eventually shut off the power, and the woman was allowed out of her car. The driver was a bit shaken, but she was said to be okay. A woman inside her car. Police did not know if the wire was live, so they ordered the woman to stay inside the car to avoid contact with the ground. Then they shut down the entire intersection. The driver was trapped for nearly 2 hours until ComEd crew showed up. The car to avoid the woman to stay inside. Police, a woman inside her.
Why is it that she's safe while she's on the inside?
It's just like the airplane example you've been describing. She's basically just in a shell that's taking all the electricity for her, so she won't get hit even if she's touching it.
Okay, even if she's stuck in the inside of the metal, she's gonna be fine.
Exactly.
Right, I'm gonna give you 5 votes. What else can you guys come up with? She is safe because come up with something else other than what Ian said.
We're looking.
Yeah, go ahead.
Oh, yeah, sorry. Like, could it like matter on the wheels too? The car wheels, the rubber maybe? Because isn't like rubber a good like conductor for electricity? Like,
Okay, so rubber is not a good conductor, right?
Oh.
It's an insulator. So you're saying that they're because of the rubber tires, right? She's protected. All right, so I'm gonna give you 5 points for that one.
Car. Police.
All right, is she safe because of the rubber?
For us to explain.
Caleb, what is it that you're saying?
Are you looking for us to explain why if she? Are you trying to look for why if she touches the metal that she still would be like okay?
Okay, I mean, whether she's touching the rubber or not, besides the point. She's safe on the inside, so the question is why, right? So they're, hypothetically, I think Ian and you guys kind of came up with it. Most people think that she's safe because of the rubber tires. This is a common misconception. Rubber tires really don't have anything to do with what's going on here. Remember, this is a live wire going up, touching the metal casing of the car, and then coming down and touching the ground, guys. This is a complete circuit. This car is part of the circuit already. This car is much of the part of the circuit as a guy who's being electrocuted on the electric chair. All right? It doesn't matter that the guy on the electric chair is wearing rubber shoes. It doesn't matter because it's part of the circuit. Current is going to go through it. In this case, the current is going through the car. This car is completely electrified. So the question is, why is it that she's not getting shot? All right, so the Ian...
more conductive.
I'm sorry, Ian, what did you say?
Because the metal is more conductive.
Because the metal is more conductive. Some of you guys will claim, and I know what you guys will claim because I've been doing this stuff for almost 15 years. The part of the reason a lot of you guys think that she's safe on the inside is because she's not touching any metal on the inside. She can touch all the metal on the inside. It makes no difference. Forget about touching the metal. She can lick the metal if she wants to. Imagine that she's got a metal fetish, right? She's going to go, lick the metal. It makes no difference. She can touch the metal on the inside. She's going to be fine. She can touch the outside metal. She's still going to be fine. All right, so why is it that she's going to be fine if she's touching the metal on the inside?
I think it's like you said.
Go ahead.
So just like you said for the electric chair, wood is a bad conductor. So when you get electrocuted in the electric chair, the wood doesn't want to share the charge at all. So you're taking a lot of it. But since they're in the metal car, even if she were to touch the metal, she would be part of it. So the electricity freely flows through the electrons. Is that close at all?
Yeah, Caleb, I like your response. Actually, hold on to that. I'm going to give you 10 points for that one. All right, you said something which is going to become useful at some point. I think you guys kind of understand the question now. So you're inside metal containment, whether it's a car or an airplane. Despite the fact that it's metal, there is current, electricity is outside. Whether it's a current wire or it's being struck by lightning, you would be safe, even if you're touching the metal on the inside. So the question is why?
Come on, please help me out.
Yes, we'll carry you.
Hold on. I got struck by lightning.
Yes.
In August 2003, Matt Thompson was hit by lightning in the hills outside Keystone, Colorado.
A bolt of lightning taken straight in the chest. The direct hit traveled all the way through Matt's body.
I had no clue what happened.
Matt's story was big news. On websites worldwide, the issue was raging.
You almost died.
Was Matt's metal tongue stud the reason he was struck?
So my tongue ring.
I don't know, dude. You might have swallowed it.
Let me see. Where's your tongue? Let's see.
Oh, it's broken off in there, it looks like. Crazy.
Body jewelry attracting lightning strikes?
So does metal on your body attract lightning? What do you guys think?
No, because there's more resistance between you and the metal than it would ever care about. Like, it would never get to that point. Your body's the limiting factor in the resistance.
Okay, so Matthew, I'm going to give you 5 points for it. So what you're saying is your body is a lot more resistant
Yeah.
to electricity. So unless the metal is the one that's taking a hit, it's not going to make that much of a difference. All right, that's one way of looking at it. What else? Does metal on your body attract lightning? Like coins in your pocket, earrings, tongue rings, keys.
I don't think it's like a big enough surface. Because you think of like lightning rods, for example, they're like ginormous. They're like 20 feet taller. Think of like on top of Sears Tower. They're like huge things. Like small little things are not going to like attract electricity like how an electric rod would.
All right, so Bailey, you're saying that I'm going to give you 5 points. You're thinking that the size may matter, right? You're thinking that the size is going to matter. It's metal. You're thinking maybe more attractive, but the amount of metal that you can carry on your body is not going to be that big. All right, so let me confuse the hell out of you briefly. All right, so I'm just going to play games with you for a while. All right, does metal attract lightning? Yes or no?
No.
Okay, so who said no? Does metal attract lightning? All right, Ian says no. The metal doesn't attract lightning. Okay, lightning rods, are they made up of metal, plastic, wood?
Metal.
They're made up of
Metal.
metal, right? Okay, what's the purpose of a lightning rod? The purpose of a lightning rod is to attract lightning, right?
Right.
Oh, if that's the purpose, what do you think works better? Is it metal or is it wood or is it porcelain?
It's metal, but it's got to be grounded.
All right, so does metal attract lightning? Yes or no?
No.
Ian, I think I have to kind of beat you up a little bit. You're digging in. Does metal attract lightning? What do you guys think? It needs to be grounded. So if the metal is up in the air like an airplane, it would never get struck by lightning, right?
Fuck.
Did I just give you an
That
answer?
doesn't.
All right, so the metal itself, does it attract lightning? All right, so Ian said no, and so he tried to defend that position.
It's not the metal that attracts it. It's the ease of resistance. It's that it's easier to go through metal than it is to go through water droplets if you're a cloud, because water has more resistance than the metal. So it just
Okay,
takes.
so Matthew, are you saying that if it's metal, if it gets struck, it's going to get to the ground easier? Is that what it is?
Yeah.
So given a choice, the lightning is going to look at metal in a tree and say, okay, if there's metal nearby, I'm just going to take the metal?
Yeah.
Is that what the lightning does?
I think so.
Are you
That's
sure?
why, that's why it strikes planes. I would say.
So you're saying that the metal attracts lightning, right?
Yeah.
So
Once it attracts it, just happens to be easier for it to go through.
okay, and that's the reason why the metal attracts lightning, so it's easier for it to go through, right? So the metal on your body, is it possible that it can also attract lightning? Bailey says the size matters. What do you think?
I would say that no.
Are you size sensitive?
I'd say that since it's not making it easier to go through down to the bottom, it doesn't make any difference. I mean, sure, it decreases
Yeah,
the.
but remember what you said like 5 minutes ago? You said no because it's more difficult for it to get to the metal through your body.
Yeah, no, it might make it easier once it gets to that part of the
Yeah,
tongue.
but
It
okay.
might be slightly easier for it to move from the top of your tongue to the bottom of your tongue, but the rest of it's still the same. It's still a great resistance. So I mean, it might have an easier time, but I don't think beyond that it would.
So would you consider a human body a resistor or a conductor?
Resistor.
You would think the human body is a resistor,
I'd say it has a lot of resistance.
like an insulator?
Yeah.
Is
At
that
least
what, guys? All right, it's not bad, guys. I just talk at this point, so we'll make the corrections as we go along. All right, Matthew, give yourself 5 points for the discussion. Let's talk about Gauss, man. Let's talk about Gauss. What did he do? Gauss made life easy. How so? We're going to talk about Gauss. Let's talk about Gauss the right way. All right, last week, I really didn't want to do this. That's the reason why I actually did it at home first. Okay, let's check to see. And then, normally I would do this in class. And this sort of derivation takes about 20 minutes, half an hour to get to explain everything. Didn't try this. And this is one of the few times you get to use calculus in physics. The way we use calculus in physics, not the way we use calculus for more advanced mathematics, high level courses. But notice that we use this next action to create that. And this is going to allow you to be able to do this. I'm not going to narrate it all the way through. It doesn't matter. I just want you to just watch this. Watch it. This is the model. that the surface area will be the same. Guys, that's 2 pages of work. 2 pages of work. Now, what Gauss did, he came up with a better way of solving this problem. In fact, his solution is so simple and so elegant. That's the reason why we're going to be talking about Gauss. All right, were you guys able to see the previous one?
Yeah, I couldn't hear anything you were saying, so I hope it wasn't important.
Ask my wife. She doesn't hear anything I say either, so it's never that important. All right, I'm preparing for a relationship, so don't worry about it. All right, so having said that, now, you guys have seen the work, right? It's 2 pages of calculus. In my case, normally if you do the integral, it's going to be 3 pages long. Now, Gauss is one of those mathematical geniuses. All right, this guy's a German giant in mathematics, one of the best mathematicians who ever lived. Einstein's idol. And he's so well recognized that notice that the German currency has his picture. All right, so
We can't see anything right now.
All right, damn it, people. You guys are really demanding. Oh, shit. We're going to just find before you said something. All right, so. All right, can you see this now? Yes or no?
Yep.
Can you guys see these?
Yep.
Right. If you can see it, that's fine. All right, then check to see what it is. All right, I can see it. All right, so that's this guy. All right, so we're going to make life easier for us. Instead of using a lot of fancy calculus, we're going to end up using. All right, so he's a German mathematician. One of Einstein's heroes. Obviously, in Germany, he's so well recognized that you can see his picture on their currency. So what he did, basically, he's going to give us the Gauss's work. And so what is the Gauss's work? Okay, ignore that one. Gauss's law is going to work on the principle of flux. So what is flux? All right, so let's stop at this point and go to the lecture notes. Just go to the module or modules, and let's find today's lecture material. Gauss's law. All right, so find the lecture review material. That's one of the things, and that's what we're going to follow.